Okay, so before we get into this presentation, I want you to suppose that you find a sunflower in the wild. So the petals of the sunflower grow so that they overlap as little as possible so that every petal can get to the sunlight. So we can ask, how does the sunflower know what angle to grow at and what angle is it? Well, we can find that this angle is 137.5 degrees. But why? Because obviously it makes no sense if we don't know why. Well, that is part of this presentation, which is going to be on the golden ratio in nature. So firstly, we want to ask, what is the golden ratio? Well, you might have seen this around the classroom and in places around the school. So it's written as this Greek letter called phi, and the reason we write it like that because it's a really nasty looking number if we don't. Okay, it's never ending like pi. So it's 1.618, so on, so on, so on. And it was first discovered by the ancient Greeks and documented in the 3rd century BC by Euclid, who is responsible for a lot of the geometry work that you do nowadays. And it's said to represent proportional beauty. Okay, so for those of you in Key Stage 4, you might have studied proportions. So when it comes to proportional beauty, this is the ratio that you would see such a thing in. Okay, and that just means it's very aesthetic to look at. And it's also the solution to this quadratic equation, x squared minus x minus 1 equals 0. But how does it actually relate to nature? Well, before studying that, we can look at the Fibonacci sequence. Now, you might be well aware of this sequence because it is famous, and it's given by the sequence of numbers is given by adding the two numbers before a number in the sequence. So if you wanted the 5th, for example, you'd add the 4th and the 3rd together. And it looks like that. So 1, 1, 2, 3, 5, 8, and so on. And this is an infinite sequence, so it never ends. Well, you might ask, well, what's that got to do with anything? Well, if I take two numbers that are next to each other in the sequence and divide the bigger by the smaller, you can see in the picture that they slowly start to look more and more like the golden ratio. So what we say is that this new sequence that we've got actually tends to the golden ratio. So eventually it will look so much like it that you won't be able to tell them apart from just looking at them. So now we've got this really strong link between the golden ratio and the Fibonacci numbers. And we can see it in nature. So if you look at the pine cone in the top right of your screen, and we're looking at the spirals of it. So in the clockwise direction, there's 13. And in the anti-clockwise direction, there's 8. Well, what do we know about those numbers? Well, they're both Fibonacci numbers. So if you divided through by them, it'd look similar, or be a similar number to the golden ratio. And that's the same that you can see with the sunflower head there, with the spirals of the seeds. So 34 and 21 would close approximate the golden ratio. And you can also see it in that very weird looking broccoli on the big left of your screen. So we can also get something called the golden rectangle, which is a rectangle that has proportions of the golden ratio. So if the length of one side is 1, then the length of the longer side would be phi, the golden ratio, or 2 and 2 phi, and so on and so on. And you can see there, when we take that red square, that we get this green rectangle. And that green rectangle will again have the same proportions. So we can keep doing this, and it will always be the case. And then we can make this really nice looking spiral from it if you take a quarter circle through each of the squares. And that's called the logarithmic spiral. Now you can see it everywhere in nature. So if you look to the top right of your screen, you can see something called a nautilus shell, which is essentially an octopus in a shell. Now it grows in this pattern of the spiral, and you can see it again in the bottom right in a hurricane, and in the bottom left in a galaxy formation. Now if it's in a galaxy formation, it's not just related to the Earth, it's related to the universe. But finally we can see it in the body. So for those of you who are looking at the right of your screen and thinking that looks familiar, it probably does, because it's Leonardo da Vinci's Vitruvian Man, one of his most famous works. Now what is said to be the case with this drawing is that the body parts are in proportions of the golden ratio, and it suggests that the human body has proportions of the golden ratio. So for example, the total height of the person is equal to 1.61, which is an approximation of the golden ratio, times the height from your feet to your navel or your belly button. Now it's also seen in our DNA, so the length and width of your DNA helix would divide to give an approximation of the golden ratio again. And finally, you can see this really strange looking mask on the left of your screen, created out of loads of different shapes. Now these shapes all have the proportions of the golden ratio, and this is called the Marquardt beauty mask. Now the person who invented this, Marquardt, has stated that those people who have facial structure similar to this are the most beautiful looking people. And when you map this onto someone's face, if you adapted their face to fit this, it would be the most beautiful that they could look. And when we see celebrities, a lot of celebrities actually fit this pattern. So now we have to look at why. Why does this actually occur? Well, we can express the golden ratio as this really strange looking fraction, okay, called a continued fraction. And all this is it's a number plus a fraction over a number plus a fraction plus a number of a fraction, and so on and so on and so on. Now if the number is rational, so it can be written as a fraction, a normal fraction, then this will stop at some point. But because phi is irrational, this continues forever, it is infinite. And the significant thing for phi is that we get these continued ones occurring, which means that it converges very slowly to a fraction, aka it is very hard to estimate as a fraction. And it is actually the hardest of any number to write as a fraction or to estimate as a fraction. So we say that it's the most irrational of any irrational numbers. So if you don't know what an irrational number is, it's a number that cannot be written as a fraction. We've got a whole number on the top and the bottom. So a better example that you might know better might be pi, that you use when you're calculating area and circumference of your circles. And because it's the most irrational of all the irrationals, this is the main reason given for why it occurs so often in nature. So if you think back to that sunflower petal example that I showed you, if you want the petals to overlap as little as possible, then you need to go around the centre point of that circle at some fraction of 360 degrees that is going to make that happen. So you want a number that is very difficult to express as a fraction, because they're not going to overlap as much. So this angle would be the golden angle. And from that, at the bottom of your screen, that calculation shows it to be 137.5. So now we know why that occurred. Okay, so what are the actual reasons behind this? Well, like we said, why we see phi so often in nature is because it's the most irrational of all the irrational numbers. So if a natural process wants something to help it grow and aid its growth, then doing it in a way that seems very random is going to help it. And we've seen that something that is very random would mean it is hard to estimate. And phi is hard to estimate as a fraction, so that's why phi is seen so often. And we could use something called Markov's theory for rational approximations, which I won't go into because it's far beyond the scope of key stage 3 and 4. But we could use it to show that the golden ratio is difficult to approximate. And it has been shown that there's a link between this and plant growth. But some people do suggest that it's just purely a coincidence, that it doesn't really have any link. And they would suggest this because we do only see approximations of it in nature. We don't ever see the specific ratio. And they also argue that whilst it may look like the golden ratio is there to the naked eye, when you actually study it, the ratio is not the golden ratio. So this is one application of mathematics in real life. Although it's not proven, it can be seen to occur in nature, and it's fascinating to see that it happens in galaxies, it happens in the human body, and so on and so on. Now the fact that it's not proven doesn't mean we can't say it occurs. It just means that somebody hasn't shown it happens yet. But the people that showed it, have shown things and proven things, have all started where you are right now. So maybe one day you could go on and prove something in mathematics. Thank you for listening, and I hope you enjoy the rest of your day.